Welcome to inverse trig functions. All right, so we're going to do a quick review about regular inverses, what are inverse functions in the first place, and then use that to introduce what inverse functions will look like for trig. Let's go over to this function. This is the function x cubed, the cubic function. It just means you just cube all the values, and it kind of looks like this. Well, it has an inverse function of the cubed root of x, which can also be written with a rational exponent of x to the 1/3. This is the same as the cubed root of x. Now notice a couple things here. First off, there's a sort of symmetry. The orange graph is just the blue graph reflected across this diagonal line, y equals x, okay? And then just the whole thing about inverse functions is that they undo each other, okay? So inverse functions, right? If I have an inverse function, they undo each other. So like f of f inverse of x, you can think about them, f and f inverse kind of canceling out in a sense. This should undo each other and just be left with whatever we have on the inside. All right, and then also f inverse of f of x should also undo each other in any order. And we can see this in a couple of different ways. Like, for example, if in our case that we're looking at on the graph, right? If I cube something and then take the cubed root, these cancel each other out. We always just get the original input. So that's what inverse functions are all about. If some function has a value of y, we can also think about it. What if we take the inverse function of both sides? The inverse function of both sides undoes the function on the left, and now we have the inverse function on the right. And we do that all the time. We use inverse functions all the time. We just don't think about it. Watch this. How do I solve this equation? The answer is inverse functions, right? What's being done to x? Adding 5. What's the inverse function for that? Subtracting 5. So we apply the inverse function, we subtract 5 to both sides. This is inverse function. That's using an inverse function. Or maybe I'm solving an equation, right? And I have x cubed equals 8. Well, how do I solve this equation? I take the cubed root of both sides. That's using an inverse function. Fun fact, there are actually 3 cubed roots of 8, but one of them is 2. That's the principal cubed root. This red thing right here, whoa, it's an inverse function. We use inverse functions all the time. Inverse functions are especially useful when solving equations, something that we're going to probably do a little later on. Okay, so this is a whole lot of things about inverse functions. One other time you might have seen inverse functions is maybe you're solving this equation. But when you take the square root, you actually get a plus or minus here, which is something a little weird. And fun fact, x squared doesn't have an inverse function. And there's something that you may have heard about inverse functions, and that's called the horizontal line test. Because look at this property, this graphical property. Well, if we try to do this, graphical property for x squared, then what we actually get, if we try to use this property on x squared and we rotate it, we get that reflection. Notice something about this orange inverse. This orange inverse is no longer a function. This orange inverse function, it is that reflection across that diagonal line, is not a function because it doesn't pass the vertical line test. So a function only has an inverse if it passes what's known as a horizontal line test. If there's any horizontal line that crosses a graph more than once, it's not going to have an inverse. So for example, right, if I look at this function, this doesn't have an inverse because it fails a horizontal line test. Here's a horizontal line that crosses the graph twice. Fails the horizontal line test. Another example, absolute value of x. This doesn't have an inverse, fails the horizontal line test, crosses twice. That doesn't have an inverse. Let's see something that does have an inverse. 1 over x has an inverse because any horizontal line you draw only crosses this graph once. Let's look at sine. Does sine have an inverse? Oh no! This is bad. Why is this bad? I want to introduce inverse trig functions to you guys. For a function to have an inverse, it has to pass the horizontal line test. Not only does sine fail the horizontal line test, it literally fails it infinitely often, forever. Imagine that. You don't just fail it a little bit. Sine is failing the horizontal line test infinitely often. That's a new kind of F. Okay? So that's where that's the real tricky things when we talk about inverse trig functions. Is unfortunately, none of these trig functions pass the horizontal line test. So what do? We're going to turn out to do the same thing that we do with x squared, right? The inverse of x squared is almost the square root of x. What do? To find the inverse, we restrict the domain. So as long as we restrict the domain of our parabola, now we can talk about inverse functions. So that's what we're going to end up doing with sine and cosine. We're going to restrict the domain to make them pass a horizontal line test. Okay, so that's a big introduction. Let's get into some more concrete things and get into some lingo. All right, and then we're going to come back to this issue of restricting the domains once we have a little bit more concrete stuff to work with. So let's kind of summarize this thing a little bit. When we look at sine, we always look at sine of an angle, and sine of an angle gives us a ratio, right? Sine of pi over 6 would be 1/2. That's sine of 30 degrees, 1/2. The ratio of the opposite side to the hypotenuse is 1/2, right? We also could look at, right, sine of 45 degrees is 1 over root 2, which means the ratio of the opposite side to the hypotenuse is 1 divided by root 2. So the main thing here, right, is that sine, as its input, it takes in an angle. An angle goes in, and a ratio comes out. So with inverses, inverses are all about switching inputs and outputs, right? If I plug in x into a function and I get out an output of y, that's the same as an output of x with an input of y for the inverse function. Okay? In fact, when you're graphing, one way that you can graph an inverse function is literally just switch all the x and the y coordinates. This has an x, y coordinate of 2, 4. So this has one of 4, 2. Switching x's and y's is what inverses are all about. When you're solving to find an inverse function, the way you do it is literally replace all your x's with y's and vice versa and solve for y. Okay, so if we switch all of our x's and y's here, we have an inverse function. We're going to call that inverse sine, like this. And if I take the inverse sine of the opposite over the hypotenuse, then that spits out an angle. Okay, so here we have a ratio as our input, and we get an angle as our output. That's how inverse trig functions work. And again, this right here is called inverse sine, or arcsine. It's often called arcsine. I love arcsine because I don't have to worry about exponents. All right, and again, as a small like notational thing, just like, right, f inverse of x is not the same thing. It's not actually a negative exponent. So similarly, right, sine inverse of x is not just 1 over sine. Right? 1 over sine is cosecant. So just be careful that sometimes negative exponents mean denominator. This is not an exponent. I didn't make the rules. I don't like the rules, but I am going to follow the rules. Okay. And this is the fundamental thing about our inverse trig functions. Okay. And we could extend this fact up here. We could extend this to every single trig function, even the reciprocal functions. But we don't really ever do that. Okay. We're mostly just going to be talking about arc cosine, arc sine, arc tangent. Inverse cosine, inverse sine, inverse tangent. We'll be using those two things interchangeably. Okay. One more comment. Inverse sine of x is also called arc sine of x. These mean the same thing. Just two names. We'll be using them both interchangeably. They're identical. Inverse sine, arc sine. Same thing. All right. So let's do an example. And then let's go back to that little pesky problem of not passing the horizontal line test. Example 1. If the sine of pi over 6, also known as 30 degrees, is equal to 1/2, and the cosine of pi, also known as 180 degrees, equals -1, and the tangent of pi over 4, also known as 45 degrees, whoa, what happened there? Equals 1, then find, or let's not find, the question is, what do we know about inverse sine, inverse cosine, and inverse tangent here? And the answer is going to have to do with what we mentioned in the last page of we're switching the x's and the y's, right? The input is a ratio. Sorry, the input is an angle and the output is a ratio. So for inverse sine, we're just going to switch that. All right. So if sine of pi over 6 equals 1/2, that means arc sine or inverse sine of the ratio is going to equal the angle. There's some caveats about this, but we're not going to bring them up yet. Similarly, if cosine of pi equals -1, then arc cosine or negative cosine of -1 equals pi. Again, for regular trig, put in an angle, get out a ratio. For inverse trig, put in a ratio, get out an angle. And lastly, if tangent of pi over 4 equals 1, then arctangent or inverse tangent of +1 spits out an angle of pi over 4 radians. All right, that's the example. Ta-da! Let's go back to that pesky little issue of horizontal line test. We're going to talk about restricting the domains of inverse trig functions. Let's start with sine of x. We talked about the graph of sine of x, and we said, okay, it goes from -1 to 1. So let's zoom in a little bit, and has a period of 2 pi. So I want this to be 1 to 1. I want this to pass the horizontal line test. That's what 1 to 1 means. So I have to restrict the domain so that we do pass a horizontal line test. So when we restrict the domains, we're going to try to keep things centered at 0 if possible, and we're going to prefer positive things over negative things. So, for example, it wouldn't really make sense to restrict it from 0 to pi. right? This wouldn't make sense. This is not one-to-one. This is not how we want to restrict our domain. So, oops. So what we're going to do, right? We're going to restrict our domain. If we're between these 2 points, we have all the outputs and all the important inputs. Well, all the important outputs, and then we're going to restrict it like this, okay? So we're going to restrict sine of x from negative pi over 2 to positive pi over 2. So sine goes infinitely long, but we're just restricting it right here. This is what we use. This is our domain restriction so that it's now 1-to-1, and this is what we'll look at for an inverse function. So what we're going to do is kind of make a table of the trig functions. And the domain restriction. All right, so we started with sine of x. We're going to restrict the domain to negative pi over 2 to positive pi over 2. Because if we do that, we have all of the outputs. Negative 1 to positive 1 is those outputs. And it's now 1-to-1. Let's do the same thing with cosine. See what we have to restrict the domain of cosine in order for it to make sense. Let's change this to cosine. So this is no longer a good domain restriction, right? It's not 1-to-1, and it doesn't have all the values between -1 and +1. So we like to have things centered at 0, but cosine, to get the different values, actually has to start at 0 and go all the way to pi, right? We have to go from here to here. And this gets everything. So that's 0 to pi. Whoa, that's the wrong button. We're going to use 0 to pi right here. And now cosine is restricted in a way that it's now 1-to-1. It passes the horizontal line test. Cosine's restricting from 0 to pi. And then tangent. Let's look at the graph of tangent and let's do the same thing. Tangent of x, Tangent of x failing the horizontal line test. But notice if we just look at a single piece of tangent, each one of these pieces passes the horizontal line test. So that piece is just from negative pi over 4, negative pi over 2, pi over 2. Like so. Now we have a single piece, this single piece. It doesn't actually include pi over 2, it's undefined at pi over 2. So here it's going to be negative pi over 2 to positive pi over 2. And this is going to come into play, especially when we get into some more complicated things. But in the meantime, this is where we're going to restrict our domain. And why this matters is doing things by hand. Calculators are actually going to come in real handy in this section. This domain restriction, all of these domain restrictions, these are all the ranges of inverse trig functions. Right? Inverses are all about switching x's and y's. If x's are the domains of the original function, then y's are the range, right? So the domain of sine is the range of arc sine. Okay. Let's see. That's kind of the most important thing that we need to talk about in this video. Let's just go to this one last comment then, and then we'll be done. Okay. So as long as we're in this interval, right? For angles in these intervals. Whoa, that's not how you spell interval. That was terrible, Jason. For angles in these intervals, the sine of arc sine of theta cancels out completely. And so on, right? The arc cosine Or wait, hold on. This doesn't make any sense. Arc sine doesn't take in theta. I need to switch this around. Sorry about that. Remember, regular trig functions take in angles. Inverse trig functions take in ratios. So what we're going to have to say is arc sine of sine of theta, they'll cancel out perfectly. Right? Arc cosine of cosine of theta is going to cancel perfectly. Arc tangent of tangent of theta is going to cancel perfectly. But if we're outside of these intervals, weird things happen. Okay? Theta outside these intervals, weird stuff happens. And that's what we have future videos about. Okay? Especially when we get into composite functions. That'll be 8.3.4 and 8.3.5. But in the meantime, that's inverse trig functions. Here's your crash course in it. Don't worry, we're going to talk about it a lot more with future videos. Let me know if you have any questions, and good luck.